So in the last review on correlation, we'll study some bottom-up approaches towards computing and modeling financial correlation amongst different variables. Now, a very important concept is that of creating copula functions. So many a times we want to calculate the correlation between two variables A and B, and we don't exactly know the behavior of these variables, or we know that these variables follow some distribution, a random distribution or any kind of distribution. So a correlation copula is created by converting two or more unknown distributions that may have unique shapes. So this variable A may follow its own probability distribution, B may follow its own probability distribution. The idea to understand the correlation between the variables A and B is to create a correlation copula, that is, convert these unique distributions and map them to known distributions with well-defined properties such as a normal distribution. Of course, there will be an approximation. So if A is following some unique distribution and so is B, then we first map them to an approximate normal distribution, and then we try to see the correlation between the variables A and B. So while maintaining their individual margin distributions, a copula creates a joint probability distribution between two or more variables. This is accomplished by mapping multiple distributions. So those multiple normal distributions are then mapped into a single multivariate distribution to create a joint probability distribution of the two or more variables. Now there'll be a lot of terminology and a lot of notation. I don't expect that to be directly tested. We'll just quickly go through it, but I don't really need you to remember or memorize any of these. Just broadly understand what the copula function process is trying to say. Detailed calculations and maths is beyond the scope of the curriculum, and for like 4 or 5 variables I don't expect anything to be exactly tested on the exam. So the following expression defines the copula function that transforms an n-dimensional function on the interval 0 to 1, that is, to a one-dimensional function. C0, 1 n-dimensional is being transformed, that is, a conversion function converts this n-dimensional function that is in the range of 0 to 1 to a one-dimensional function. So suppose GI/UI defined between the range 0 to 1 is a probability distribution, that is, the probabilities can be between 0 and 1, is a univariate uniform distribution, that is, it can take on n values. Then a copula function C can be defined as the copula of various such distributions wherein we first, that is, the copula of or the joint probability distribution of various such uniform distributions can be calculated with the help of an inverse function or inverse cumulative normal distribution. So remember, the first step is mapping this unique distribution. In this case we've taken the example of a uniform distribution. So the first thing we do is to map it onto the cumulative normal distribution, and then we estimate the correlations between the different variables, the variables I from 1 to n. So G1, let's say, is our first variable, G2 is the distribution of the second variable, G3 is the distribution of the second variable, of the third variable, so on and so forth. Copula function creates the joint probability distribution of these individual distributions, these individual uniform distributions. How do we do it? How do we create that copula? First, the individual distributions are mapped to a normal distribution or a known distribution with well-defined properties. For example, here we are taking a normal distribution. F represents the cumulative normal function. So we first convert them into an approximate normal distribution, that is, see where the corresponding percentiles lie or corresponding quantiles lie with regards to a normal distribution. Then, using the correlation between the variables, or the approximate or the known correlations between the variables, we try to map all of these variables or all of these normal distributions into one n-variate normal distribution. First, we convert these uniform distributions into their individual normal distributions, and then we combine these normal distributions using the correlation between the variables into one normal distribution, and that will be an n-variate normal distribution, which will give us the joint probability. And we'll understand this better with the help of an example, but very important to understand this basic process of creating a copula. So different variables, let's say interest rates are there, stock prices, commodity prices, and various other financial variables are there. Now we want to see the joint probability distribution of a given loss in a particular year, which will be dependent on interest rates moving in a particular way, commodity prices moving in a particular way, stock prices moving in a particular way. How can we compute this combined probability distribution? First, we convert the distributions of interest rates, commodities, stock prices from whatever form they may be into an approximate normal distribution. Then, this is the first step. The F inverse that you see is converting each of these individual distributions into a normal distribution. Step 1. And then we combine those normal distributions into an n-variate distribution to see the joint probability of the three variables behaving in a particular manner and giving us the probability of particular outcomes. Now, what is the probability of so much loss given that the three variables can move in this particular way as defined by their normal distributions, which we got from their original distributions by an approximation. First convert them into normal distributions, then combine them to create an n-variate normal distribution. So once again, the GI UI or G1 U1 is the marginal distribution, Fn is the joint cumulative distribution function, F inverse is the inverse function of Fn. So this joint cumulative distribution is a known distribution. For example, as I took the normal distribution, rho f is the correlation matrix structure of the joint cumulative function Fn, that is, this represents the correlation between these different variables. So this copula is translated as follows. Suppose there are n marginal distributions, that is n individual distributions. A copula function exists that maps the marginal distributions via this inverse function and then allows for the joining of the separate values to a single n-variate function that has a correlation matrix of rho f. So I expect this definition possibly to be directly tested, so you must understand what is the process that we are trying to accomplish. Detailed mathematics I don't expect to be asked on the exam. So a Gaussian copula is where this f is a normal distribution basically. So a Gaussian copula maps the marginal distribution of each variable to the standard normal distribution, which by definition has a mean of 0 and a standard deviation of 1. The key feature is preserving the original marginal distributions while defining a correlation between them. The mapping of each variable to the new distribution is done on a percentile to percentile basis. We'll explain that with an example. So variables of two unknown distributions A and B have unique marginal distributions, and we will convert them into an approximate normal distribution first. So this was my variable A, this was variable B. both of them had independent distributions. Now what I can do is that I can take the 5 percentile value. I can see where is the 5th percentile of the value, or what value is that. And then in my normal distribution, I will ensure that the 5th percentile value is the same. Let's say this was the 5th percentile value. So even in my normal distribution, when I'm mapping, I will make sure the 5th percentile value is the same. Similarly, I'll make sure the 10th percentile value is the same. Of course, there will be some mismatches because the exact same distribution can't be replicated. We are trying to get to a approximate normal. We're trying to impose a normal distribution on this. So I will give some parameters, that is keep some values the same, so that the approximate normal distribution can be derived. Similarly, I'll do it for B. Keep the 5% value the same, keep the mean of the same. So the mean should be the same. The 95th percent value should be the same, so that I can get an approximate normal distribution, or I can map these A and B into an approximate normal distribution. The reason I'm doing this is because I need the joint probabilities. Let's say A, for instance, is a distribution of interest rates, B is of stock prices. I may need to see that what is the probability that interest rates and stock prices move together, or both fall, or both go up, or one goes up, one goes down. Those probabilities to study, I need to see that what is the probability that A takes a particular value and B takes a particular value. So I do that by first converting them into approximate normal distributions, the F inverse part, and then combining these normal distributions into one combined probability distribution. So what is the combined probability that this and this happens, or what will be the value under extreme circumstances? So 9% of the times interest rates can have so much loss, stock prices can have so much loss. So 5% of the times combined loss can be so much. But of course that is dependent on the probability or the correlation between the two. So we also need a correlation matrix to combine these two normal distributions or unique univariate distributions into one multivariate distribution. So in the above figure, the 5th percentile observation for marginal distribution A is mapped to the 5th percentile point on the univariate standard normal distribution. This is repeated for each observation on a percentile to percentile basis. Same is done for marginal distribution B. The new joint distribution is now a multivariate standard normal distributions. The unique marginal distributions of the variables are not well behaved. However, the standard normal distribution is a well behaved structure. Therefore, a copula is a way to indirectly define a correlation relationship between the two variables. So the copula is defined as the joint standard multivariate normal distribution, which comes by combining these individual normal distributions using a correlation matrix into a multivariate normal distribution. So a univariate normal distribution is converted into a multivariate normal distribution that gives us the joint probabilities or the combined probabilities, and we'll understand that better with an example. So once again, the correlation matrix is the n into n correlation matrix for the joint standard multivariate normal distribution. So if there were 5 different variables, interest rates, n is the number of independent distributions or the independent variables. So interest rates, stock prices, commodity prices, implied volatility, and let's assume oil price separately we are considering as a variable. So let's say these are 5 independent variables. So we will need a correlation matrix before we can construct the joint copula, or the copula rather, the joint distribution of these 5 independent variables: interest rates, stock prices, commodities, implied volatilities, oil price. So Gaussian copula is a common approach for measuring default risk It's especially used for the purposes of default risk. That is, what is the probability that all these variables will move adversely, or will move or will decline by a certain extent. That can be done with the help of this Gaussian copula. So again, the same equation that we've been studying. So marginal distributions of cumulative default probabilities are mapped to the single n-variate normal distribution Mn with a correlation structure of rho m. The exact same thing that we've been studying. The term n inverse maps the individual default probabilities or the individual distributions on a percentile to percentile basis on the standard normal distribution, and then this Mn combines these standard normal distributions using the derived correlations between the different assets to give us a joint probability distribution, or the joint default probability distribution. Only thing in this case, now the probabilities are default probabilities. So let's see how we can apply this approach. Suppose a risk manager owns two non-investment grade assets, that is speculative grade assets. Table below lists the default probabilities for the next 5 years for companies X and Y that have X and Y credit ratings respectively. How can a Gaussian copula be constructed to estimate the joint probability of the default of these two companies in the next year, assuming a default correlation between X and Y is 0.05? So basically, how exactly do we apply what we talked about in the previous slides in the real world? So the probability that X will default in 1 year is so much. Probability that he'll default in the second year is so much. Probability he'll default in the third year is so much. Fourth year is so much. These are not cumulative probabilities. These are marginal default probabilities in a particular year. So if he survives the first year, 8% chance he'll default in the second year. 6% chance he'll default in the third year. Similarly for Y, these are the default probabilities in the given years, marginal default probabilities. So this distribution per se may not be normal. So what is the first step? First step is we'll map both X and Y into approximate standard normal distributions. How will we do it? We will convert the cumulative probabilities and make sure that in the normal distribution also the 5th percentile value, the 10th percentile value are the same, so that we get the same approximate normal distribution. So in this example, there are two companies X and Y, so we need a bivariate normal distribution at the end, and the default correlation of rho, which is given to be 0.05, can be applied. So it's only two companies, only two variables, only one correlation coefficient is needed. We don't need n into n correlations, and the correlation matrix will not be needed. So first thing is that we will do the percentile to percentile mapping of the cumulative default probabilities for each company to a standard normal distribution. So the probability of default in year 1 is 0.077, year 2 is so much. Cumulative default probability we can calculate 16% that either in year 1 or 2, or rather by year 2 he would have defaulted. 22% chance that by year 3 the company would have defaulted. Again, add the marginal probability. 33% chance that by the end of 5 years, it's a speculative grade bond, that the bond would have defaulted. So for this particular percentile, we'll compute the standard normal variable. So if we take the standard normal distribution, then a 7.7% probability, or a cumulative probability of 7.7% implies a value of minus 1.426 standard deviations from the mean. 16.1% will imply minus 0.99. 0.33 will imply a value of minus 0.432. Similarly for Y, we can calculate 32% chance that it will default in year 1. So the cumulative normal variable comes out to be minus 0.465. By second year, it comes out to be 52.2%, 32 plus 20.1. 52.2 means it's slightly on the right hand side. For the third year, 67.6%, that is 0.457. So we're just trying to understand the cumulative normal distribution and the probabilities of default for the individual variables x and y, or individual bonds x and y. So columns 3 and 6 represent the cumulative default probabilities for companies x and y respectively. The values in 4 and 7 map the respective cumulative default probabilities to the standard normal distribution, and this can be calculated using the Excel function. So the joint probability of default for both x and y defaulting within 1 year can be calculated. There is the joint probability of bond B also defaulting and bond C also defaulting, rather x and y both defaulting, can be calculated as the probability of x being less than equal to minus 1.426 and xc being less than minus 1.46, given a correlation between the two of 0.5. This correlation is not 0.05, it's a correlation of 0.5. So for bond X, the probability that both of them will default in the first year will come from the joint probability. The probability of X is minus 1.426, probability of Y is minus, or X being less than minus 0.465. So Y has a much higher probability, X has a relatively lower probability, less than minus 1.426. So what is the joint probability of these two events given a correlation equal to 0.5? Again, the idea is to explain how the copula or the Gaussian copula works. Exact calculations and the maths can be solved using Excel sheets and using random probabilities and sampling. So I don't expect the numerical calculation to be asked. However, just understand what we are trying to do. So using various formal or using various softwares like MATLAB and Excel, we can generate thousands of random samples, given these are normal distributions now, or we are assuming them to be normal distributions, and then calculate what is the probability that both of them are going to be in default at the same time, given a correlation of 0.5. So again, this slide will tell us what exactly is done. I don't expect the maths to be asked, but still we'll just go through what is the, or how is this combined default probability calculated. So when a Gaussian capilla is used to derive the default relationship for more than two assets, a Cholesky decomposition is used to derive a sample joint probability from a multivariate copula Mn. The default correlations of the sample are determined by a correlation matrix M. If there are more than two variables, then we'll need a correlation matrix to define the correlation of every asset with every other asset. First step is to equate the sample to the cumulative individual default probability using the following equation. Again, we will use a Newton-Raphson search procedure, or using Microsoft Excel. We will equate the sample probability to the cumulative individual default probabilities. The random samples will repeatedly be drawn from this normal distribution to determine the expected default time using the Gaussian copula. Random samples are drawn to estimate the default times because there is no closed form solution to this equation. So of course we cannot solve it mathematically that what is the joint probability. So what we actually do is that we just conduct thousands of iterations using a normal distribution. So we input to the computer that this is a particular normal distribution, this is a particular normal distribution, this is the correlation, and the computer will generate 1,000 samples of the possible multivariate distribution, from which we will guess, okay, so this percentage of the time there will be a total default, or both are being in a default, because otherwise there is no mathematical way to simply calculate the joint probability of default. So we can't just simply apply a formula like wx square sigma x square plus wy square sigma y square, something like that, to just calculate the default probability. It has to be done more in an empirical manner, you can say, or more by conducting random samples and then counting that how many times were both in default and what is the joint default probability. That's what he says, that there is no closed form solution. So illustrate how a risk manager estimates the expected default time of asset I using an n-variate Gaussian copula. So suppose a risk manager draws a 25% cumulative default probability for asset I from a random n-variate standard normal distribution. The n-variate standard normal distribution includes a default correlation matrix that has the default correlations, and then we'll illustrate how this 25% is equated with the market determined cumulative individual default probabilities. And suppose that the first random sample equates to a default time of 3.5 years, and this process is then repeated 100,000 times to estimate the default time of asset I. So the idea is to compute the expected default time of asset I, given that the default depends on n different variables, and the default correlations with all the n different variables are calculated. So basically this is done by sampling again and again and seeing what is the default time after various samples. So in some samples it came out to be 3.5, some samples it came out to be 6 years. So we can calculate some random distribution, that is, in most samples the default time, the joint default, came out to be 3.5 years. Sometimes the default time was just 1 year, sometimes the default time came out to be 5 years. And then we can calculate a cumulative, from this distribution we can calculate a cumulative distribution, that is some probability that it will default in 1 year, cumulatively higher probability that it will default in 5 years, cumulatively higher probability that it will default in 9 years, so on and so forth. So that was about Gaussian copulas, a little bit complicated, not many examples, not many equations, not many details given on how this exactly is done, but just get the broad idea, and just make sure that a theoretical question you are able to answer given the 4 choices as far as the exam is concerned with this review. That was about correlation and market risk. Thanks a lot, and see you next time.